Okay. This is going to be nuclear magnetic resonance spectroscopy. Has anybody ever know anything about MRI? Okay, there's a big magnet, right? And it looks at what type of nucleus it is, right? And so it is a derivative technique based off of nuclear magnetic resonance spectroscopy. It is not exactly the same technique, by the way. It's more like mapping a specific response rather than looking for all the responses, if that makes sense. Okay. Okay, so this right here is actually an NMR machine right here. These can be very small and fairly weak to be extremely powerful and cause people to have like heart problems if you get too close. Okay. I actually knew a group that had a very, very powerful one. It was shielded in the room, but they were too close to the elevator. And every time the elevator moved, they could see it in their spectra. They were so pissed because they had just gotten the instrument, and it was it must have been most of the way to $1 million by the time they had it put in and shielded and all that. So and all that work and everything had been done on a room right next to the damn elevator, a giant chunk of steel that gets moved around. There's a funny story about GCMS that's just like that, by the way. I knew a medical lab, hospital, that put in a GCMS, and it was the highest grade at the time you could get, and they got it in, and all of a sudden they're seeing nicotine everywhere. Every sample, nicotine. And so they're trying to figure out what the hell's happening. Finally, they look out their window, and there was no smoking on the entire campus, okay? And they look out the window, and they notice that the campus end's a business a couple blocks away, and there's people that smoke there every day. So from then on, they just had to deal with nicotine spectra. Nicotine in every spectra. They put in a vacuum system eventually that helped, but shit. I know, right? There's actually a very famous story about the guy that discovered the radiologically dated the planet that came with that 4 something billion year. His number was actually correct, by the way, and it still stands today. But we have more decimal places that have been added to it. So, and his story is actually he got this brand new instrument, most accurate one of the day, because he wanted to radiologically date the planet to a more precise number. And then he starts trying to do it. They did it with a radioactive form of lead. And because it has just the right half-life to be able to date it, and they had a sample that they knew approximately when that had crashed to Earth, and so they could date it based off that. And so he goes to do it, and he gets lead on everything. Every single spectra gives him lead, and so he can't figure it out where the hell's the lead coming from. Lead's not exactly super common, right? And so finally he throws everything out of his lab. I'm not kidding, like literally like tears his hair out apparently and throws stuff out of the lab. And then he seals his lab and bleaches the lab 5 times, plastic wraps everything, and then brings it in one piece by piece after 5 bleaches to get rid of lead. And he finally got it. And that did it. And that's because partially we've increased the lead content of the entire globe. It used to be an additive to gasoline. And so like lead is actually is on everything. And there's also a fine amount of lead in like dust and stuff. And so it drifts around and you'd be surprised. Enough to throw off that measurement apparently. Yeah, not enough to actually do anything to us, right? But okay, folks, so anyways, this right here is an NMR instrument. And so what you're going to see here is this right here is the sample tube. Can everybody see that little thing? Like it's a very tiny little tube, right? And what this does actually, is you have a tube that goes through the center of a superconducting magnet. Part of it has been cut away so you can actually see the inside, but it would fully wrap around this, okay? Everybody okay with that? Fantastic. Okay, and so this superconducting magnet is as powerful as you need it to be. This is actually why instruments have gotten so much better for, has anybody ever seen the new MRIs? They make, instead of going, okay, everybody's seen an old MRI, right?
Yeah.
Okay. You guys are aware of those. Those are the old ones, okay? Big, long tube, right? Yeah. The new ones just have a little halo. That's it. And they make a sound that sounds a little more like pew. Pew, pew. I'm not joking. If you ever hear them running, they sound like a sci-fi show. Pew, pew, pew. Like a kid mimicking his favorite sci-fi show. Anyways, so those are the new MRIs, and what's happened is we've gotten so much better resolution that we don't need the powerful magnet anymore. We can actually weaken the magnet considerably. We've also gotten much better at making electromagnets, and so like the electromagnet can actually be smaller and thinner for that size. They also have gotten way faster. Okay, way faster. So you really just need to go whoop. Yeah.
I don't think they give you headphones anymore because it's
Oh, no.
not loud and it's so quick that it's just like,
Yeah, we probably have some new ones, especially if you go to Vanderbilt.
yeah.
I know that quite a few of the MRIs of even Vanderbilt, though, are still the old ones. So, if you get
It's
lucky.
expensive to change them out, I assume.
Yes. Kind of.
Kind of.
Yeah. Yeah. Yeah, I'm not actually as convinced that they're that expensive to change out necessarily. I think it has more to do with the laws around them,
Oh,
but I'm not an expert in that field.
gotcha.
Yeah. But like the cost to run them is incredibly high
Yeah.
for the old ones. The new ones are a lot cheaper to run.
Interesting.
So yeah, I'm actually not as convinced that they wouldn't save money. Yeah. But the upfront cost would be high.
Yeah.
Anyways. Yeah. So what ends up happening is you take your sample, you suspend it inside a magnetic field. You then apply a very strong magnetic field and a very specific magnetic field. You need to be able to control it very well. And so this sample does not get clamped in here. Anybody notice that? There's no wire or anything come down. There's nothing. Looks like it's floating in air, isn't it? Guess what it's doing? Floating in air. Yeah, you actually have an air that comes in. You blow air up, and your sample basically just floats there. You have a little ring around it usually that helps it. And so what you then do is you apply that magnetic field, and then what you have down here is you have a probe. It's going to emit and receive radio frequencies. Okay? And so normally signals come in, radio frequencies come in, and they're going to cause your nucleus to react. You usually do a little vibration, a little dance. Okay? However, if you apply a strong enough magnetic field, you'll actually line up all your nuclei. Okay? And then when you cause them to do their little dance, it's going to knock them off that alignment. And so then what's going to happen is they'll realign over time, and that's going to cause an emission of a radio signal. Okay? And so you basically think of it a bit like bowling, okay? You line up all your balls, you knock them down, and then they come back up, and that gives you your signal. All right. Okay. And so this is just a signal being generated and then taken back. This is actually one of the reasons why these machines have progressed so much, is because can anybody tell me a radio frequency signal that has tons of money poured into it? I'm talking like 100 times the investment that happened for landing on the moon. Do you have something in your pocket? Yeah. Yeah. Cell phone towers, right? And so this stuff is actually essentially like a cell phone tower. And those things have gotten so much better because they're trying to shrink the amount of the bandwidth space each customer needs so they can handle more customers, right? And their developments have just lowered the price of everything else in spectroscopy by just orders of magnitude. Incredible development. Yeah. Really cool, actually. Anyways, so right here we see an NMR spectrum. This right here is going to be labeled in what's called chemical shift, and we'll talk about that in just a second, okay? It's basically your radio frequency, but measured in a very unique way, okay? So that you can reuse it over and over and compare them. This right here is going to be your signal amplitude. Can anybody tell me what that would normally be? How well something absorbs, right? So this is how well that frequency absorbs, okay? And so very high frequency, you got more of those, right? Very low frequency, you have less. Okay, and so the NMR spectroscopy is going to use the radiation from the radio frequency. That's the RF region is the abbreviation. Everybody go with me using RF. Okay. Again, that's called radio waves oftentimes as well. In more modern parlance, RF would be much more used. NMR makes use of the superconducting magnet. This is going to subject the sample to a very high external magnetic field. This is actually going to be abbreviated B. B is magnetic field, and then EXT for external. Okay. Why do we have to say BEXT? Do atoms have magnetic fields? Yeah, they definitely do. Because they're little magnets, aren't they? Yeah, little positive cores with a negative outside, right? And then you have atoms that have lopsided nuclei. So their magnetic field's actually going to change whenever they spin and move, which is going to be very important. So most NMR spectrometers are going to take advantage of the fact that the portion of the RF radiation absorbed by the sample at each frequency is actually remitted at the same frequency. And so what you absorb typically is going to be what you re-emit. Okay? This is true for most substances. There is transitions where you can have a transition where you absorb one and then re-emit at lower, but those are actually fairly uncommon and rare. Okay? That's actually what the ground's doing, by the way. So like the ground, when you look at it, it's a darker color, right, than the surroundings, the air. And that's because it's absorbing and not re-emitting in the same frequency. Okay? It actually re-emits in infrared mostly. So the magnitude of the oscillating RF radiation re-emitted from the sample is going to be recorded over a period of a few seconds. It's going to be digitized. It's going to produce what's called a free inductive decay, FID. And this is one of the reasons why I'm going to teach you something that apparently a PhD in chemistry did not know and gave me as a review comment on one of my papers once. Okay? Infrared spectroscopy and NMR are not the same thing. So infrared spectroscopy is an absorptive spectroscopy. It absorbs a frequency and then it remits that. Okay? This is a decay type spectroscopy. And so it's a time sensitive spectroscopy. Okay? Meaning that you actually put it in a state, you knock it off the state, and the thing you're actually looking at is it coming back to that state. Okay? And so it's decaying from a higher energy state. All right? So one looks at the energy going in, one looks at the energy coming back off. Right? And so they're very different types of spectroscopies. If you try to use every single piece of what you know from NMR to do IR or vice versa, it's not going to be a one-to-one. Okay? So many IFD are typically going to be acquired and they're going to be averaged, after which you're going to use a mathematical algorithm. It's called a Fourier transform. Anybody ever heard of Fourier before? Okay. No? All right. So this is actually a mathematical transformation, and it's not just spectroscopy or chemistry that uses this. Like your graphics cards do it. You can do it on a picture if you get like a graphics editing program. You can do a Fourier transform. It's actually much more common than you think. Okay. So this is going to decompose the FID into its individual frequencies. These are called signals. If you were actually to look at this FID, what it would look like is something like this. And those that have nothing to do with frequencies. Okay? And that's because it's actually a decay pattern. Right? But if you use a Fourier transform, you can actually extract out of that information the frequencies. Okay? Or I should say, it has everything to do with the frequencies, but it looks nothing like you could understand as a human. Yeah. If you're wondering, a Fourier transform for something that's actually extremely simple, if you did this by hand, would take you about 6 months working 12 hours a day. Anybody want me to sign one? Yeah. So back before computers were widely available, this was something that spectroscopists would have to do. They take like one spectra and they do the the Fourier transform, and then they'd get the spectra from it, and it'd be this long multi-month process, and it'd be awful. Yeah. So a lot of people didn't use Fourier transform back then. Nowadays, with computers, it does it in seconds. Okay. Really fast computer can do it in microseconds. So let's talk about a bit about nuclear spin and your nuclear magnetic resonance. So without being subjected to a strong magnetic field, a sample is not going to absorb RF radiation and cannot produce an NMR spectrum. So if you look at a proton, it has spins that are plus 1/2 and minus 1/2. Everybody remember your electrons? Anybody remember quantum numbers at all? No? Okay. Okay. So suffice to say, when you have a nucleus, okay, it can have a up, where it has the spin going this way. Okay. Right hand rule. Anybody ever heard of that before? Okay, so that would be the right hand rule. Spin's going this way, and so you have a up spin. Spin's going this way, you'd have a down spin. Okay? And that has to do with the magnetic field around it, and it is the alpha spin state or the beta spin state. Another terminology for that is the plus 1/2, minus 1/2. Okay? And that's the two spin states you're going to find these nuclei in. In a typical substance that you just get out in nature, there are exceptions where these spin states can actually be aligned to some degree. But typically, these are just randomly everywhere, and so you have no overall state. Okay? And so you're going to see something like this in nature usually, where you sort of just have it pointing in every direction possible, and you have no overall spin states at all. Okay? And so if you throw radiation in there, RF signal, it just gets scattered every way. You have no overall spin state to absorb in one frequency. Okay? This is actually what helps these substances break apart radio frequency signals. It's because they're absorbing a bunch of different ones, because they're all different states. So this is, again, going to be your alpha and beta spin state. And so what we can do is we can actually apply an external magnetic field, and we can go ahead and line the spin states. And so, for example, we apply external magnetic field where our magnet matches up with the alpha spin state. And so what you would see is the vast majority of these are going to go ahead and snap into the alpha spin state. So the positive end matches our external magnetic field negative end. Negative end of our atom, positive end of our external magnet, right? And so we snap them all into one state as the preferred lower energy state. Okay? Now when you have a low energy, high energy states, not everything's going to be in low energy, right? At room temperature, some of the stuff is going to be in the high energy, isn't it? Okay. And so you'll have some atoms in the higher energy state. Okay, and that's your background. And then what you would do is you're going to go ahead and throw in an RF signal. Okay. This is going to match between the energy of these two states. And that's the delta E of the spin. Okay. So the delta E between the alpha and beta spin states. Is that making some sense? Okay. Okay, so you go ahead and match that with a radio frequency signal. What's going to happen is you're going to have a portion of your lower energy state go to your high energy state now, right? You'll invert it. Okay. This is now in a high energy state, and so what's going to happen is over time, this is going to slowly decay and relax. Everybody remember your kinetics? You had like a logarithmic, right? So this would be that logarithmic. So we're going to go down fast, and then we're going to tail off, right? And then we'll reach a state that we never actually reach, right? And so this would be where it flips back. This radio frequency is going to be re-emitted out, and then we're going to get back to our ground state. Everybody okay with that so far? Okay. Okay, and so this is what you would see on the spectra. You see a signal amplitude again, so it absorbed at this radio frequency, and you get your chemical shift here, which is again a way of denoting those frequencies. Okay. In this case, because our magnetic field is setting everything up, we actually have a lot of variability here. Okay? Like if you were to do an NMR on different days, different times with a outlet, do you guys know anything about electricity? Okay, does anybody know how many volts comes out of an outlet?
150.
Okay, it's called 120 nominal. But the real answer is anything from 110 up to 130. And so if you take electricity and you try to run an electromagnet off of it, that magnetic field changes all the time, right? Because your electricity coming in is changing all the time, right? And so you can clean up that electricity, but you can never get it perfect. It actually has pulsing frequencies. Okay? And that's the hertz of the electricity if you ever do anything with electricity in your house. Yeah. That's actually, anybody know what split phase is? Oh my God. You guys are killing me. Okay, everybody's aware there's a 240 volt that you can get in a house? Like the dryer, right? Yeah. Okay. And it's that 3-prong thing? Yeah, big one. Okay, so that is split phase is what that's called. What's happening is electricity comes in and frequency. Okay? And so what they do is they line two different frequencies together for that live power, the one bringing in the electrons through, and the difference between the magnitudes of the peaks ends up being 240. Each line would be 120. And then the neutral, which is that normal other plug, yeah, that is actually at your 0 point. Typically tied into the ground somewhere in your house. So it's what's called ground, or grounded. Yeah. Not in multiple places, though. The ground actually is different electricity and different volts. So if you ground your house to different places, you'll actually have a continuous electrical flow. Did you guys know that? Yep. Especially with some of the soil around here being acidic, you can get very different electrical flows. Yeah.
Wait, what's scary?
And funny enough, because of the capacitors from the wire in your house, because you have a bunch of wire tucked away in places, you can actually run LEDs in your house when the switch is off. As long as it's not a switch, then wire to the LED. If it's that, then it won't run. If it's a wire coming in, then the switch, it'll just continuously run. Yeah. Anyways, I actually had one room in my old house that I had to get special LEDs just so that wouldn't happen. Yeah, because it like always run my LEDs at just a little bit. Yeah. Okay, is everybody good with this right here? So you got them aligned, you split those two states, right? So they're energetically different. The alpha state matches your external magnetic field. The beta state is the opposite, right? So it's higher energy now. And so what ends up happening is your frequencies of your RF radiation will match that difference in energy. That will boost them up. And then you're going to keep it real quiet. Anybody know how you can quiet a room from radio frequencies? Okay, anybody ever heard of a cage? Yeah, you can make a cage out of conductive material. And you can actually get those for like your phone, little pouches that you can put them in and it'll cut it off from signal. Yeah. People get them so they don't get monitored. Really. And so you boost up to higher energy. By the way, stronger magnetic field, what would it do? Come on.
Would it separate them more?
It would, right? This would become higher energy, this would become lower energy, right? And so you'd get more separation, and so you can have a larger difference between these, right? Meaning a higher frequency, higher energy one, right? Okay. Okay. And so you can also tell bigger differences between things. So like you separate this out, it gives you more spots you can be in, right? Yeah. So, okay. Anybody have any questions? Fantastic. All right, so when the beta state returns to the alpha state, your RF photons are going to be given off, and that signal can then be detected. Signal is going to appear as a peak in the NMR spectrum. The RF radiation can therefore be used to study the nuclei of protons. Protons are not the only nuclei that can be studied in this way, of course. However, the most common usage of it is probably HNMR. Okay? And that's the one we're going to start off with, you all. But it is not the only nucleus that can be detected by whatsoever. It's just the easiest one. Little question here. How would weight affect this? Mm-hmm. So if I try to shift my energy state of my little phone, right? Not difficult, is it? I try to shift the energy state of this desk. Yeah, it's going to be much harder, right? And so I need a bigger, stronger magnet. Okay? Yeah.
Will that affect the relaxation? Make it quicker or take longer? Or not really?
It depends on the magnet
Okay.
and your weight of your nucleus. But the decay pattern is going to be the same overall. Because remember, it's the same order decay that you would see for like nuclear. And so like you'll half your population within your half-life.
Right.
And so you'll see that same sort of pattern every time. Okay. So the nucleus is going to be NMR active, and this can be studied with NMR spectroscopy if it has an odd number of protons, an odd number of neutrons, or both. The important thing is it has to be uneven somehow. Okay? Can anybody tell me why that would be? Okay. What if I take something that's entirely even, if this had no markings on it, and I spin it? Can you really tell the difference between the different sides here? No, you can't, can you? But if I take something uneven, you can tell the difference between the sides, can't you? Okay? And so if your nucleus is even and symmetric around it, you can't tell the difference when it spins. And so you can't detect it. If it's uneven, you can tell the difference. It's going to generate a magnetic field you can detect when it does the spin. Okay. Okay. And that happens anytime there's an odd number of protons or an odd number of neutrons or both. You end up with an odd number that can't be arranged symmetric, right? Okay. Okay, and so right here we actually have our magnetic fields. We need to talk a bit about shielding, chemical distinction, and the number of NMR signals. And so right here we have an atom that we're looking at here. Here we have an external field, right? Be external. Everybody okay with that so far? That's our magnet around it, right? Our superconducting magnet. Okay. Okay, so what are we looking at whenever we're looking at an atom? Well, we're looking at a nucleus and it's going to have quote-unquote spin. Okay? And then we're going to have electrons, and those are also going to be moving around, right? And so a very easy way to sort of think about them is to think of them like planets orbiting the sun, where they also have their own little spin, okay? It's a nice analogy, and mathematically it works very well. But I'm going to tell you it's kind of bullshit. But we don't want to go ahead and go into a harder model now. This is an easy model mentally that we can work with, okay? So let's just go ahead and use that. Is everybody okay with that? Okay, so does anybody know what happens when you have a moving charge? Anybody ever taken like a copper tube and dropped a magnet through it? Or seen that demo? Oh, this is just sad. I need to do a bunch of like basic physics demos. Okay, so is anybody aware that like power lines give off a radio frequency? Yeah, and you guys have probably like went under power lines, the large ones, and had like broken up conversations. Yeah. So that's the same thing. You have electrons moving through a wire, right? And them moving through that wire actually creates a perpendicular magnetic field. Okay? And so that's what we're seeing here. This is again the right hand rule, the direction you're going. You would then use your right hand, and that would be your magnetic field around that. Okay? Okay, and so that's actually what we're seeing here. As the electrons are moving around our nucleus, they're generating their own magnetic field. This magnetic field here is actually going to end up blocking off some part of our external magnetic field. Okay, it's going to depend on how well that nucleus is shielded, right? Which has a lot to do with how much electrons is around it, how much electron density there is. Okay, everybody okay with that so far? All right. You all had kind of talked about this before. You may have remembered in general chemistry, you would have had something where you did the trends on the periodic table. Okay? And as we went to the right on the periodic table, everything got smaller. It got better ionization energies, right? Hard to take the electrons off. As we went down the periodic table and to the left, had the opposite pattern, right? Okay. This is actually because of the same thing. It's actually shielding, but it's done because of the stuff inside the core electrons. Okay? So as we build up core electrons, they actually shield the rest of the electrons from the nucleus. So that was a similar shielding effect. All right. So what we get right here is, again, the magnetic field from our shielding here. This is going to subtract off the external magnetic field, and this is going to give us our magnetic field effective, what the nucleus actually experiences. Okay? Everybody okay with that so far? I lose people. Fantastic. Okay. So again, we have our local magnetic field. That's the magnetic field in this case that's causing the shielding. Okay? It's going to be opposite of the magnetic field external. It sometimes will actually be aligned. Okay, we'll talk about a couple of cases of that, but it's fairly rare, right? Typically, this is going to cause shielding. So the magnetic field that's felt by the nucleus is going to be your effective magnetic field, BEEFF, effective. So BEFF is going to be somewhat less than the B external in almost every case that you're ever going to encounter. It's going to be extremely rare for you to have one that's higher than the external. It'd be very unusual. And this is called shielding typically, or that it is shielded. So you say that the nucleus has been shielded. It is the proton is shielded, and this is typically by the electron density around it. Or the B local, the magnetic field local. So each chemically distinct type of hydrogen atom in a molecule is going to give rise to individual signals in a proton NMR spectrum. And this is because the effective shielding on each, right, is going to be slightly different because they are going to be in different environments. They will have different amounts of electrons around them. Okay? Remember where we talked about electron density, especially where we were talking like polarity? Yeah, that's that same trend, isn't it? Okay, we're just subdividing our polarities now. Okay? Okay, so let's go ahead and look at some examples. Now, because your magnetic field is always varying all the time, and it's actually, you could get RS close enough that you could do this, but your magnetic fields are very difficult to hold in one place and get repeated. So what you always do in NMR is you always use a reference signal, okay? And this is almost always TMS, excuse me, which is tetramethylsilane, okay? So tetramethylsilane, TMS. This is what it looks like right here. It's 4 methyl groups off of silicon. And you'll see that this is extremely shielded, right? Got all these methyls contributing electron density around silicon, right? Okay. And so this signal right here actually shows up at 0 ppm. You always add a little bit to every single sample that you run in an MR. And that gives you a peak that you know shows up exactly here. Notice all your hydrogens are chemically the same. Okay? So they all show up in one spot. All right. All right, and so that gives you a nice reference signal right here. We always put that to 0. So you assign that as your 0 point. And then everything that's off of that is said to have a chemical shift, and that's going to be measured in ppm. Okay. Okay, and so right here we can see 2 very distinct hydrogens. Everybody see it okay? Fantastic. Now, this one right here is attached to an oxygen, isn't it? Okay, this one right here is attached to a alkyne. You got it. Yeah, triple bond, right? And so what we're seeing here is this has a lot of the electron density pulled off of it, right? And so it has very little shielding. Everybody okay with that right there? Okay. This one, on the other hand, has a lot less of that electron density pulled off of it, doesn't it? Okay. Now, it actually does have a little bit more complications here, and that's because you have the pi bonds that'll be generating those magnetic fields right next to it. Okay, the delocalized electrons. But we can see very distinct signals. What do you notice about the intensities, by the way? They're very different as well, aren't they? Yeah, despite the fact that they're one hydrogen, they're quite different, aren't they? Okay, so be careful when you're looking at intensities for NMR. All right, so right here we have several different protons. And again, we can see that as we go away from a functional group, we can have less and less interference on it. We can also see a distinct set of nuclei there, 2 hydrogens that have the same peak. Okay, and so we have peak A here, which is this one here, which is off the triple bond. This one over here is off the triple bond, but it's also next to a Br, a bromo. This would be called an alpha hydrogen. Everybody okay with that? Meaning it's the next group over. Okay? Beta would be the next group after that. Gamma after that. Okay? Okay. Notice again, these right here would be called equivalent nuclei, wouldn't they? They're the same conditions. Okay? And so they are equivalent. They'll show up at the same peak right here. All right, so let's consider the number of HNMR signals that should be generated. Determine which spectrum, 1 or 2, was produced by dichloroacetic acid right there. So how many hydrogen peaks should show up? Anybody know what this acid's used for, by the way? No? Anybody ever heard of taproot removal? Or seaweed skin peels? That's this. You can use laser as well. This is more gentle and just fades it. So then you can cover it up with stuff usually. Also been used in cancer treatments. It's theoretically useful for cancer treatments. They're studying it. Okay, so how many peaks should we see? Two. You got it. Very good. Yeah, yeah. And that's because we have two chemically distinct peaks, don't we? One right here, one right here. Very good. Very good. Okay. So let's talk a bit about molecular symmetry and chemical equivalence. So if we have symmetry, then those are going to mean that we have chemically equivalent peaks on both sides, don't we? Okay. So for example, these H2 right here are symmetric and they're going to be chemically equivalent. But these ones here, this CH2 and this CH2, they're also the same, aren't they? And so they're going to be one set. Okay. And they'll only show up as one peak, right? Okay. And so we have another set here, and then another set right there. And so we have sets A, B, C, and D. And it's the exact same thing on the other side. Okay. Okay. So how many distinct types of protons are there in the following molecule? So we're looking at a symmetric set, right? Okay, so right down here. Okay. All right. And so can we rotate this? Yes, we can rotate that and it'll match, right? And then like this, right? And so we have chemically distinct peaks only on several of these. You will notice that you have the CH3s right here, right? I only have to do half the molecule. These are different than these. And so that's 1, 2, 3 sets. This doesn't have any hydrogen, so we skip it. And then we come up here, right? And that would be our next set of hydrogens. And notice again, they're a little bit different than these ones, right? See that? So that right there is a tertiary carbon, right? 3 other carbons attached. And so that has a different group that's attached to. Okay? Or another way of saying that is it's kind of like isomers, right? Do we have distinct groups like when we generated our isomers? Okay, would that be chemically distinct? Yeah, that's chemically distinct. Okay, and so we have our 4 different groups right there. So for each hydrogen atom in question, we draw a complete structure of the molecule with just that hydrogen atom is replaced by imaginary atom X. If the X substituted molecules are either identical or enantiomers, then the corresponding hydrogen atoms in the original molecule would be chemically equivalent. If the X substituted molecules are either constitutional isomers or diisomers, then the corresponding hydrogen atoms in the original molecule would be chemically distinct. This is the very, very long way to do this. Okay? But if you're not sure, this will always get you the correct answers, assuming you do the whole thing. Okay? Okay. So right here we see another example. And so if you wanted to double check, are these chemically equivalent, we'd replace each position with an X, right? And so we replace this with an X. And that's chemically unique, isn't it? Okay. We go over here and we place one of these with an X, and that's chemically unique, isn't it? Okay, we go over here and do that, and that's not chemically unique versus that one, is it? That would give you the other chirality, wouldn't it? And that's it. Okay. And so what if we then replace this hydrogen over here? Well, that one's chemically unique, isn't it? Okay. Okay, let's try this out. So use the chemically distinction test to determine how many chemically distinct hydrogen atoms there are in chloroethene. So you'll want to draw that out and try to determine how many chemically unique hydrogens there are. By the way, you guys probably know this chemical. This is vinyl chloride. Anybody ever heard of PVC? Polyvinyl chloride. That's the monomer for PVC. Yeah, you just do addition reactions. I know. It's like all the stuff connects back to your lives. I'm gonna go ahead and put it on. Does everybody have the polyvinyl chloride or the vinyl chloride? Okay. Okay, I'll go ahead and put it here in case you need it. So that's what you're going to be drawing out and trying to do here. And this is a very like entry level on just learning this stuff approach to it. It's not what I would recommend using once you've got it down. After some practice, you'll be able to do this without doing that. And you would only need to do this if you're really unsure. Okay. All right, let's go ahead and move on forward. So what we'd end up doing is we do this right here. So this right here is the vinyl chloride, right? Okay, and we got 3 hydrogens on it. And so we need to see here, are these chemically distinct? And so we would replace each one by X. And so we put X here, and that's our trans, isn't it? We put an X here, that's our cis. And we put an X here, and that would be geminal, wouldn't it? And so are any of those the same? No. So A and B are actually diisomers of each other, which is one of the things that are chemically unique, right? And then the last one's actually a constitutional isomer, which is also chemically unique. Okay.
Why aren't they enantiomers then?
Because they're not mirror images.
No.
Yeah. So not mirror images. That's that cis trans. Yeah. Oh, I'm sorry. Did I say enantiomers?
Yeah.
Diisomers.
Okay.
Diisomers. Yeah. Yeah. I guess I was back here mentally. All right. Okay. So again, when you have HNMR in all NMR spectroscopy techniques, they are going to be time scale dependent. And so your axial and equatorial H atoms are going to rapidly interconvert. And what you're going to end up seeing is that, yes, they would be chemically unique between those two, but because they're conformations, you're going to get rapid inversion. And so that signal is essentially going to get garbled. And you're just going to get one peak from those two. Okay? So, yeah, those are chemically distinct positions, but it's because they're conformations, right? And conformations are going to go back and forth. Okay. All right. And so, for example, right here, we actually see the CH3 here. Again, it would be chemically distinct for this hydrogen if you just look at that structure, right? But again, what we notice is this right here can freely rotate around that bond, can it? So that's a confirmation. That's not an isomer, is it? Okay. And so that gives us one peak here. That's going to be the blurred average of those. Okay. Of these three hydrogens. Because they'll just continuously rotate. And again, remember that we've knocked something up and it's decaying. So that entire time it's decaying, it's rotating, right?
So there are two distinct hydrogens, but because it's rotating, it's showing it as one.
Yeah, we would have two distinct hydrogens here if you could freeze that. Yeah. And so like if you freeze it with a ring or double bond or something, you could see those. But as it is freely rotating, can't see them. And that's why the wording for that previous method, where it was isomers, right? Constitutional isomers or disomers. Yeah. It avoided the confirmation. Yeah. Okay, and this is that other hydrogen right there, by the way, the OH. And then TMS, right? You're actually starting to see some other indicators, by the way, of other things that we're going to talk about a little bit later. Okay, so right here, some different characteristic chemical shifts. And we'll start talking about the inductive effects and magnetic anisotropy. And there's TMS, of course. It's always 0 because everything's measured off of it, right? Okay. Okay, we'll call that a day, and I'll go ahead and start on this next time. You all have a wonderful day, and I will see you Wednesday and Friday. Okay? Don't forget, we'll be going on to the next lab activity. That is the next formal lab report. That one prep extra good because if you can do that without much help, any significant help, you can actually go ahead and not have to take the lab final. That will count as the lab final. Okay? No. So experiment 45, we're doing a formal lab report for it. But we also have what's called a lab practicum this semester, right? And that's that final week, during finals week, we would have to do that unless you do experiment 45 without needing significant amounts of help.
41.
Yeah, the next one, I'm sorry, 41, yeah. Yeah, thank you. Yeah. So if you guys can get through that without significant help, that you no longer have to do a separate practicum. It'll count as it.
Is our next exam Monday or?
Yes. Yeah. I think so. We'll have to see if I can finish this on next lecture. Yeah.
So the next exam is going to be 15, 16, 17?
Yep, you got it.
Mhm.